Welcome to the 83rd Theoretical Physics-Colloquium by Professor Rogier Windhorst from our Arizona State University. He received his PhD in 1984 from University of Leiden. Afterwards, he had several postdoctoral positions, Carnegie Postdoctoral Research Fellow at Carnegie Observatory in Pasadena between 84 and 86. Then he was project scientist at the California Institute of Technology between 86 and 87. He joined ASU in 87, and he's a full professor since 1997. Since 2008, he is also a co-director of the ASU Cosmology Initiative at the university. He received numerous awards over the years. He was, as I mentioned, Carnegie Fellow, first between 84 and 86, Alfred Sloan Research Fellow between 89 and 93. He became Regents Professor of Astronomy at ASU in 2006 and Foundation Professor in 2008. He served in numerous scientific and advisory committees, working groups, review panels. He's very active in professional service. His research interests include astronomy, cosmology, galaxy formation and evolution, the cosmic dark ages, and the epoch of first light, astronomical instrumentation, and many other things. And today he's going to be talking about James Webb Space Telescope status as of 2021, and some of its first signed programs, faint object time domain, cluster lensing, and caustic transits. And with that, I'll give the microphone to Roger.
Thank you, Igor. Thank you, everybody, for having me here. So my apologies that this is as non-theoretical physics as it gets. It's very hands-on with hardware and then some applied science, which I think you'll all be very interested in. But it's a little bit off from the regular topics in the excellent series that Igor has been diligently organizing. So the first half of the talk is all about the hardware, and then I'll briefly pause for questions. Of course, you can also ask questions on the chat, which I may not see, but Igor will interrupt me. And then the second half is about the science. I have too many charts, so I'll speed it up and skip a few charts here and there as it go. I decided not to cut them out. So today, the Webb science remains as compelling as it was 20 years ago. In fact, I think it is even more exciting today than we could have imagined or planned for 20 years ago. There's a link to the talk here, which I think I put in the chat, but you may not all have seen it. Igor got it to work, so he can forward this to you guys. The charts are all public. I'm not talking about anything that's proprietary. So the topic for today, I will try to consistently use orange for Webb and other colors for other things. So we talk about the hardware update as of this fall. And I've been saying for over a year now that we're going to launch this fall. And for the previous decades, you know, the launch date was 2011, then 2018, then 2020, and now it's 21. It's actually no longer in the fall. We launch on December 22nd, which is technically winter. But anyway, there we go. Second topic. We'll talk about this time domain science. So variable active galactic nuclei. My apology for the various acronyms. Those are supermassive black holes that feed. Then, of course, very high redshift supernovae, and also the very dark sky in the north ecliptic pole time domain field. This time domain field is in the region in the sky, not too far from Polaris, but near the ecliptic pole that you can observe all the time. So if you owned the telescope, you could point there all the time and do whatever you like. It's also in the continuous viewing zone of Hubble. So Hubble has extensively observed it too with the same purpose. So as long as the mission lives over 5 years, which is the requirement, up to 14 years given its propellant lifetime, we can do a lot of time variability studies there. And then third, we will monitor the best lensing galaxy clusters for possible caustic transits. I'll explain what that is. An oddity of Einstein's theory of relativity in the case of strong gravity, strong lensing, is that you can get magnifications of very small objects that are nearly infinite, not quite. And therefore you can turn this telescope, instead of a 6.5 meter telescope, you can turn it into something that's 10 or 100 times larger for a brief moment, a couple of months. And then I'll talk about how we do this science. So this is just a reminder, this chart, and Igor, tell me if I talk too quickly, that both Hubble and Webb have been alive as projects for almost 20 years before launch. And then, of course, Hubble is now almost in its 32nd year. So these projects are easily, you know, a good fraction of a human career, half a century in the case of Hubble, start to finish. And Hubble still has a few more years to go. I got this chart from Jim Westphal's office at Caltech. He obviously wrote it for HST, but you get old before you know it in these projects. So the Hubble Mirror is a little bigger than the size of a human being, 2.5 meters across, while the Webb Mirror is 2.5 times larger, still 6.5 meters across, 18 hexagonal mirrors, each 1.35 meters in diameter. That means since the resolution goes as lambda over d, this telescope, Webb, will 2.5 times better resolution than Hubble at the same wavelength. They got a small wavelength range of overlap. And then, of course, roughly the same resolution as Hubble at 2.5 times longer wavelength. So it's an infrared telescope designed to observe with Hubble's resolution or better. It will go up on December 22nd, Wednesday morning at 5:20 in the morning, if all goes well, on an Ariane 5 launch vehicle. We selected that in the early 2000s, 2003 to be precise, because back then we thought it would have the most number of successful launches by the time we were to launch. And that has indeed been the case. There have been more than 125 successful launches on an Ariane 5. Only the first one failed. So we sit inside the top of the launch vehicle with the sides of the telescope folded up here. It's folded up like the giant wings of a bat, 6,500 kilograms, with a propellant tank that's fully loaded. Once we leave Earth in this gravitational landscape, schematically shown here, and get past the orbit of the moon, which is this white circle, we get not quite drawn to scale, about 5 times further away is a second Lagrange point in the limited 3-body system. So Sun, Earth, and then the spacecraft. We go around the Sun every 365 days, of course, with the Earth. And because we generally look in the anti-Sun and anti-Earth direction, both the Earth and the Moon and the Sun will always be behind our sun shield. Therefore, this is the darkest spot in the solar system we can easily lay our hands on to put a large spacecraft in there. The second Lagrange point, unlike L4 and L5, which are stable, L2 is not stable. So you need to use a little propellant to make sure you don't drift out of here. And to do that, you describe a Lissajous figure around that hypothetical point every few months, and every few weeks you use a little propellant to correct your course. Otherwise, you will drift away and start orbiting the Sun. From this vantage point, you can observe the sky 70% of the time. Not every point of the sky. Sometimes you have to wait for the Earth and the Sun to get out of your way to see a target. So this was, as of the spring, well, the good summary of everything that has been built. Of course, it has all been assembled and shipped right now. So 18 of these primary mirror segments, a secondary mirror here in the lower, I hope you can see my cursor, lower left, before it was gold coated. And by the way, we use gold coating for all the mirrors, not because the project has so much money, but because gold is highly reflective in the infrared. Like, you know, my wedding ring shines yellow because it's gold, and it reflects the light at 98% barireflective surface in the infrared, not in the optical. And that means it makes a very effective infrared telescope, since in many of the instruments which are shown in some of these packages over here, you got 14 internal reflections, all gold coated, to optimize the throughput. We're currently filling the propellant tank in Kourou, French Guyana. Of course, at some point we'll be 100%. We're actually a few hundred pounds underweight, and that's good for the launch. So we'll have a full propellant tank when we go. This is what was assembled in the last decade, all the parts. The primary mirror segments here, a baffle, we call it the doghouse, that prevents us from seeing stray light, secondary mirror here, instrument package here, the spacecraft underneath. The light, of course, comes from the left here, hits the primary mirror, then reflects off the secondary mirror, then goes to the doghouse into this phone booth size, it's actually the size of a minivan, where the 4 scientific instruments sit. So that was designed 20 years ago and built, finished in the last 15 years and tested in the last 5 years, just to give you the high level view. This is the real thing. This was not a very popular statement of me to make, but I asked John Madden, the Nobel laureate, about 10 years ago, can we have something to cover up our mirrors in case the launch is delayed and we stare at the ceiling for 5 years? And their response was hell no. And then eventually they changed their mind. And so here we have 2 Olympic divers on diving boards. Well, they're Goddard Space Flight Center employees that very carefully lift these mirror covers away from the telescope. And they were on there for a number of years just to protect the optics. You can see the gold-coated mirror segments there. This is the whole thing, not the whole telescope, the whole observatory, but the whole telescope ready to go in Building 29, the largest building that Goddard Space Flight Center has in Maryland. Once upon a time in the 1980s, Hubble was tested out here as well. You can see the NASA logo here on the wall, the NASA meatball, and it's on a merry-go-round telescope, so you can test it every which way. And so the next picture shows the team with, John Mather, the science lead here, cracking the whip. And you can now see that the wall with the NASA meatball is behind us, and it reflects in the telescope. So that's the NASA logo reflected in the telescope. And it magnifies. So the telescope works, to first order. Of course, it doesn't work to the level here that we want it to work in space. So that had to be tested. You can see the whole crowd over here when the picture was taken. So this telescope then in the last couple of years has been tested every which way. And before we get to that, I will give you a brief summary of the scientific instruments we have. So it roughly works from 0.7 microns, which is the visual red, all the way up to 29 microns, with most of the instruments working in the near infrared between 1 and 5 microns. There is the near infrared camera made by our colleague and good friend Marcia Ricci at the University of Arizona that does imaging over a relatively wide field in near infrared. There's a near infrared spectrograph made by the Europeans that analyzes the light as a function of wavelength. There's a Canadian fine guiding sensor that has 2 probes on the side where you lock on 2 stars to hold the telescope still during the long exposure, so it ain't moving. And then there's a European mid-infrared instrument, which works between 5 and 29 microns, which is more designed to take images and spectroscopy of the chemical composition of the universe, star-forming regions in particular. So 27 US states and counting evolved, including, of course, Arizona, Canada, and more than 16 countries in Europe, and of course the launch vehicle. So a big international project, which is why we're still alive today, because we have had a few near cancellations. I will not get into the politics, that's a whole other talk, but let's say you want to observe more than an object at once, not only for imaging. Here you see a beautiful galaxy cluster. I'll get into this a little bit more. I notice Alison Noble is in the audience. She is an expert on galaxy clusters. So imagine 10 to the 15 solar masses all piled up into a mega city of galaxies over here with a couple of giant galaxies. These are excellent gravitational lensing sources. And let's say you want to observe spectra of more than one of these objects at a time. You can do this with this array of micro shutters. Each of them is less than ½ millimeter across, 0.2 by 0.4 to be precise. You can open and close them at will. They close and open mechanically with magnets. And you have 64,000 of them 4 times repeated. You can make any pattern you like the JWST logo, which is not very useful here in the lower right. Or you could open the little windows for where you know there will be galaxies. And then in the next very long exposure, you can take very long integrations and turn those images into cigars, basically horizontal spectra that almost overlap, not quite. So for every object in the field, well, not quite everyone at the same time, because some of them will overlap, but for many objects in the field up to 100, you can get a very faint spectrum. And that's a very powerful, also the most fragile part of the observatory. Some of these shutters are stuck closed, and you have to schedule around them, take 2 exposures to make sure you don't miss a galaxy. Some of them are stuck open, and to prevent stray light, they were painted over with epoxy. So here we have the thing as it was about 2 years ago, when the secondary mirror was tested. So it's folded up now, it's laying on its side in the clean room. You see all kinds of cables, and you'll see, I spare you the movie, but when they test this out, that these technicians will run around in bunny suits, not to guide the equipment. The motor is here, and here there's redundant motors, but just to make sure you offload the gravity, because all these motors need to work in 0 gravity. That means in 1 gravity, they get overstretched. So you have to offload the gravity, and that's being done here, just to make sure that the secondary mirror, which is now gold coated, comes out nicely, and it does. And then when all that was done, you know, we put the thing in a suitcase. It doesn't fit in your overhead compartment, but it goes on a 36-wheeler. It takes 2 freeway lanes, and the whole thing goes into a C5, the largest cargo plane in the world other than the Antonov. And then you can ship it wherever you want. So here is the suitcase in front of, in Johnson Space Flight Center, their big thermal vacuum chamber. This door is 14 meters. It's the largest thermal vac chamber in the world. And inside this chamber, in the 1960s, it was built back then, the moon landers and the Apollo capsules were tested, not the entire Saturn V, but the upper stage of the Saturn V. So here comes the telescope being rolled in, fully deployed, put in the chamber, and 60 meters up there is a test tower, and you can test the optical equipment. And so we remove the technicians, close the door, pump it vacuum, and then cool it down to 45 kelvins. I should have said earlier on the telescope, optimal operating temperature is 45 kelvins. And we achieved that by having this giant sun shield. This sun shield is a layer, 5 layers of Kapton. Kapton is a very highly reflective, very strong material, a little bit like your kitchen saran wrap, but much stronger and much lighter. And these 5 layers spread out horizontally with these telescoping bars here in 2 directions. And then they spread out vertically, as you will see, along vertical spreader bars with mechanics and pulleys. Here they are both folded up on 2 giant garage door size pellets before the telescope gets mounted in between. And there is the telescope, which gets mounted here on top of the sun shield, lifted from the ceiling with everything folded up. Notice that the 3 side panels on the left and right are folded backwards, and they will move forward in space, of course. All these mechanical motions have been tested extensively in 1 gravity to make sure that they work and that motors and redundant motors don't get stuck. But this is pretty much what the observatory looks like and will look like in space before that sun shield gets lifted up. And that sun shield will keep the telescope cold. Each one of these layers reduces the temperature by roughly a square root of 3. So the bottom layer sees the sun, so it's 300 kelvins. The top layer goes down to 45 kelvins. And the telescope will always be in the dark. So here's the solar panels coming out, also tested, hanging vertically from the ceiling to make sure that you offload to gravity, and there's the solar panels for energy folded up on the spacecraft. So these were a couple of last pictures a year ago during the pandemic when everything was assembled and tested. I'll spare you the details for the sake of time. But I do want to say that everything was extensively tested also for launch loads and shaking. When this happened a few years ago, it set us back half a year because some nuts and bolts had fallen on the floor. That was a bad thing that should have never happened. They had not put the appropriate amount of epoxy on the nut when it was put on the bolt, and so the nuts vibrated off. That has been fixed, of course, in 2019, 2020. Here's the last time the telescope on a transport vehicle went into the acoustic chamber and the vibration chamber. We do vibe horizontally and vertically just to make sure it will survive the launch loads. This was actually the most dangerous part, other than the launch itself, of constructing the whole observatory. Because if California, this was in Redondo Beach, had had an earthquake at that time, that would not have been good. So once it was mounted on the shake table a year ago, sure enough, they had an earthquake. The Monterey Richter scale 4, it was the El Monte earthquake of last summer. And they noticed it, of course, but it didn't do any damage. It was not a very severe earthquake, and everything was bolted down. Anyway, so here's the sun shield for the last time being folded up after they patched a few holes and tears. It's still pretty fragile material, so eventually you will get some tears in that sun shield. And this is the final stow that happened this last July to make sure that these two side panels were completely vertical, mounted next to the observatory. So there we are before we go and ship to Kourou. This was now 2 months ago, or today is December, 2.5 months ago. And since then, it took the 16-day journey to Kourou in French Guyana. And it is now ready to be launched later this month, actually precisely 3 weeks from today. So that's the first part of the hardware. I'd be happy to take a question or two, and then we'll go on to the science.
I didn't see any questions in the chat, so if anybody has any question, please raise the hand or speak up.
Yeah, the thing that I find somehow most fascinating about James Webb is this sort of, I don't know how long it is, these kind of 3 weeks of terror after you launch, where everything has to unfurl. I mean, just how terrorized are you?
Well, we are a little antsy. But we have tested and retested, and the team is confident that everything will work. Otherwise, we wouldn't launch. We had a little bit of a hiccup. To give an example, a few weeks ago, when the clamp that holds the observatory to the launch vehicle, they were actually mounting it onto the O-ring that connects the telescope and the observatory to the launch vehicle. A clamp released too soon and too sudden, and it caused a shock to the observatory. There was no optical damage, but it set them back by about 2 weeks. They had some time to spare. They needed to make sure that none of the relays or the electrical connectors had come loose. And they have ways of testing that by connecting cables and outlets to the observatory, which they did to make sure all the electrical connections were alive and produce the appropriate signals. So they have tested that. Yeah, there will be about a month of terror. It is very slow terror. It is not like, sudden things. Well, things can go wrong, of course, but it's like watching grass grow. Everything is very, very slow. I deliberately do not show the deployment movie, of which you can find many on the internet, and they are 2 minutes long. But you need to imagine that this entire process gets stretched out over a month. And then it's followed by a month of cooling, going from room temperature to 45 kelvins. And then about 2 months of wavefront sensing, where to within 100 nanometers, all these mirrors need to be precisely aligned, and each one of these mirrors has 7 degrees of freedom. There's pointing fingers behind them that do 7 different motions, namely push and pull, translation in 2 directions, rotation, and then radius of curvature, and of course tip and tilt. So they have a lot of freedom to move each one of these mirrors. So if one of them gets stuck, which we hope it doesn't, but if one of these mirrors gets stuck anywhere, the play in each of the mirrors is several millimeters, and they get launched in the nominal position, and they won't be off more than a few hundred nanometers to begin with. Then you can move the other 17 mirrors still in the right location to get a focused telescope. If 2 of the mirrors get stuck, hopefully one of the 3 redundant hexapods behind each mirror. You can, tilt the mirror completely out of the optical path. You point it at something else, so you get some stray light from it, but it wouldn't affect your images too much. That's a what if situation. So yes, we are somewhat nervous, but we've also done a decade long of testing after a decade of designing and building. So other questions? Great question.
I'm old enough to remember that first Hubble image. So roughly speaking, when will you know that it actually can be focused?
Well, we already know from the thermal vacuum chamber. We spent a fortune to make sure we didn't have the spherical aberration of Hubble, which was a grave mistake. So they put it this way: Hubble was the most precise UV optical mirror ever made, precisely to the wrong shape by mistake. Right? And they had to launch the astronauts with corrective optics to fix it. This mirror is the most precise infrared mirror ever made, listen carefully, to the wrong shape by design at room temperature. So when you sink it down to 45 Kelvin, it will have exactly the right shape. So there's almost nothing you'd have to do in terms of wavefront sensing if everything goes well. Even if this mirror, and so Hubble was a very passive mirror. It had a few support points, but they were in the nulls of spherical aberration. So there was nothing you could do to correct that error with the mirror support. Here we have so many degrees of freedom behind each one of these mirrors that if we had 5 times the spherical aberration of Hubble, we could still poke it out. Now, we don't have that spherical aberration, but if we had, or any other flaws like coma or astigmatism, we can use the hexapods to poke it out. So as long as it deploys and the hexapods, which are the mechanical fingers behind each of the mirrors, work, we should be good. Yeah, great question. Other questions?
I don't think we have anything right now.
Yeah. So here we are in the L2 Lagrange point. Sun and Earth and Moon are behind us to the right. This green band across the sky is anything we can see at any given time. So we can't actually look in the anti-sun direction because the telescope would get too cold, but we can look inside this band at any target for any length of time. Then of course, this whole green band goes around the sun every 365 days. So the entire sky will roll by every half year for about 2 months. You can point at a target. But there is a small region about 5 degrees across at the north ecliptic pole and the south ecliptic pole where you can point all the time. So if I were Bill Gates and I built a replica of this telescope and I only wanted to ever point here and nothing else, I could do that 365 days a year, 24/7. Of course, the telescope isn't going to work like that because we have to share it with a large number of people, but we are making a special purpose of that north ecliptic pole over here. It's a very nondescript region. There's really nothing there of interest, except of course faint galaxies and faint stars. It's actually not too far away from the galactic plane, about 33 degrees. So we were a little worried that we would get the high latitude galactic cirrus, which is the heated dust that boils off the plane. And so we picked a field inside this region. Rolf Jensen did that at ASU. Here's a map of 5 degrees of the star density measured with the WISE observatory, where blue is good and red is bad. So we want to have the least number of bright stars that would saturate our detector. And we found a very small region here. We call it the time domain field that also, and again, blue is good and red is bad, that has a very low dust content. To the right is a dust map. So we found a hole in the galaxy where you get less than 3/300 of a magnitude, which is about 3% extinction from the foreground dust in the galaxies. And you have no bright stars either. So that's a perfect spot to stare at for 100 hours. If you did this in the southern ecliptic pole, you'll be completely clobbered by, unfortunately, a nearby galaxy, the Large Magellanic Cloud that takes up most of the south ecliptic pole. Very interesting target by itself, but in my book, it's not really a galaxy because it's blue shifted, right? It's actually orbits our own galaxy and it's close by. It's very interesting. but it's clobbering up the south ecliptic pole. So we're not looking there, except for those people who want to do distance studies like Adam Rees. They will probably spend a lot of time. There's our north ecliptic pole field with various circles indicating the radio coverage, the intended JWST coverage. HST has covered this extensively, and all the bright stars are on the edges. We avoid them like the pest because they saturate the detectors. And in the middle is just an ordinary, collection of distant galaxies and some faint stars in the foreground. Because of the low galactic latitude, you get somewhat more than average faint brown dwarfs, which is actually very interesting in itself, right? There's a large number of observations of this field already, all the way from the hard X-rays to the long wavelength radio. I'll spare you the details. I do want to say these brown dwarfs are very interesting. We get about 5 times more than in an average field. And they're like big Jupiters, right? There are failed stars, if you wish. They have the mass of a couple of times Jupiter, maybe 10 times, about the same size. They never got hot enough inside to flare up like a star. But they have, like Jupiter has the great red spot that goes around. They're not constant in brightness. They will actually go up and down in brightness a little bit because they have atmospheric structure. And we're going to monitor these all the time. So here's a couple of brown dwarfs in the foreground, these red dots over here. This is what the field looks like from the ground. Ordinary distant galaxies, ellipticals and spirals. Our own galaxy would look like that, and so on. And so it will give us a field day to look for high redshift galaxies. This very faint red dot, if you can see it, more about it in a minute, is probably a very distant galaxy. And here's another one that James Webb will study in great detail. There is, because we're also in the continuous viewing zone of Hubble in cycle 25 and 28, we are covering it entirely with Hubble, both at the wavelengths that Webb cannot do, like the ultraviolet blue wavelengths, and a little bit in the red, so we have some baseline for the time domain studies. Here's the pattern. It looks like a Dutch windmill that Webb will observe. It's a little complicated, but you can, at any different orientation angle, lay the telescope down, depending on the time of the year, to get a windmill pattern like this. And Hubble has done that too. They are the real Hubble observations. There will be some holes in the mosaic. So unlike the Hubble mosaics, which are very dense and have almost no holes in it, with Webb, the geometry is such that you will get some holes in the mosaic. And that's because the near-infrared camera has these 2 4-chip panels that cover a small area of sky, each with very small gaps, but there is a gap in between. So when you start moving this detector array on the sky around, there will be some holes in here and there, and that's true for the other cameras and spectrographs as well. So get used to the holes. We'll make them go away in the press releases, but there will be some gaps in the data. Astronomers don't worry about that too much, but it is something. And you can just imagine that because you have the near-infrared spectrograph here that the Canadians built, where you turn every galaxy into a cigar during the exposures, you can analyze it as a function of wavelength vertically. And you get the NIRCam infrared images at the same time. You get this, 1, 2, 3 pattern on the sky that's fixed during the exposure. We fought long and hard to get this camera to work parallel to this primary camera. So we get all that data at the same time. And then if you align these properly with NIRCam, you can fill this horizontal strip at the bottom here. With NIRISS, you fill this top strip. And then when you rotate that by 90 degrees, you get this windmill pattern where everything is covered both with images and spectra to 28 or 29 magnitude for those of you who think in those units. 29th magnitude, by the way, is 10 nanogensky. And a gensky is 10 to the minus 23 watts per meter per square meter per hertz. And if you rotate it by 45 degrees, you get almost a dense speck of images in green and spectra in purple. So you get a nearly perfect data set with a hole in the middle that we'll cover up later. So needless to say that this is perfect for, like, for instance, looking at high redshift supernova. And, expansion is a terrible thing. because you get relativistic time dilation. Things happen with supernova, you know, they go off, the central star explodes and leaves a neutron star, a black hole behind, and it temporarily increases in brightness, like you see over here, a pair instability supernova, for instance, the red curve, or an ordinary type 1a that got Adam Rees and Saul Perlmutter the Nobel Prize, or a pair instability supernova for a very massive star, 200 solar masses. That's actually spread out over you know, almost 6 years, and has a very funny looking light curve. And all these, you know, to 28.5 magnitude, the bigger this number, the fainter the limit. They are detectable to JWST, but you have to monitor it for quite a long period of time and make sure that it follows one of these curves. And so to the left here is the redshift distribution, where redshift 6 here, just off the chart, is about a billion years after the beginning. And redshift 1.5 is sort of the current half age of the universe. The current age is 13.8, so about 7 billion years is in this range. And so around this redshift, that's actually where most of the effective sampled volume is for galaxies, also where the star formation rate peaks. We expect to see quite a few, of the order of several, between several and a dozen of these supernovae per year, per field. Even up to very high redshift. So all the good work that has been done with the supernova folks for expansion of the universe can be pushed to much higher redshifts, get higher precision, better understanding of the standard candle behavior of these supernovae, and so on. Very interesting topic. A number of Rees's folks like Strolzer and Rodney and Rees himself are part of this, and they're very keen on doing this. It's not my field, but it will get done. You know, stay tuned for supernova research with Webb. What's perhaps even more interesting, in my mind at least, is not so much refining the Hubble constant and refining the cosmological model with more digits of precision in all the cosmological parameters, but also look for this reionizing population. You remember from the WMAP and Planck observations that the cosmic optical depth, tau, which is the amount of ionized radiation between us and the surface of last scattering, is actually quite small. It's 0.05, 0.06. And that number, when multiplied by a constant in various models, gives you the redshift of reionization, where the universe went from largely neutral after recombination, of course, for first 400,000 years. This happened in the first billion years, where we went from nearly complete neutral hydrogen fairly suddenly within a redshift shell of about 1 to almost completely ionized. And this is a rather small range, according to the data, about a redshift 7.7 plus or minus less than 1. So about 670 million years after the beginning. There must have been this first population of ionizing sources that went off in great numbers, sufficient numbers, whether they were stars or faint active nuclei, black holes that had accretion disks. Either way, there was enough UV radiation to ionize the universe for a second time. We call it reionization. The problem with this is that it's not actually the only measurement we have. We have this other thing done at ASU by Judd Bowman, where at a redshift of 17, there is this trough in the microwave background around 78 megahertz. And I believe it has been confirmed. It's rather deep, deeper than predicted. And the most logical explanation is that it's an initial imprint of the hydrogen signal in basically the 21 centimeter line, 1421 megahertz rest frame, where the electron, when it goes around the proton, has spin up or spin down, and that causes the 1421 megahertz signal, or 21 centimeters in wavelength or energy. And that's been redshifted here to redshift 17, plus or minus a small range, a significant dip. And that would have been ionization by the first sources, probably the first stars. So how come these numbers are so different? They are enormously different. This is the first 220 million years. This is the first 670 million years. And they're both quite narrow. To make sense of that, let me put this in the context of the Hubble Ultra Deep Field. You've seen it all in its various forms. This is all 592 hours in 13 filters, properly weighted with color from the far UV to the near IR, all done with Hubble. The magnitude limits here are between 28 and 31, where 31 is a nanogensky. And for the record, a nanogensky is the brightness of a firefly if you place it at the distance of the moon. So that will be roughly, you know, Hubble's limit after 600 hours, or Webb's limit after 20 hours or so. And this was done in 13 filters. You can see there's only a few stars here, one there, one there, one there. So those are, you know, the bugs on the windshield of your car when you drive on the highway and see all these distant cities, which are the galaxies. A couple of elliptical galaxies, redshift around 1 or so, a galaxy like our own, but a few billion light years away over here. And then a lot of faint galaxies with more exotic material, including some very red ones, which are more dusty and higher redshift galaxies. If you take the same data, but render it into the infrared, this is more what Webb will see. This is actually the Hubble data, but that's, you know, 600 hours almost, what Webb will do in 20 hours or so, but longer wavelengths also. And I've now indicated the number of the galaxies at redshift 7 and 8 in green circles, redshift 9 in orange circles, and redshift 11, of which there's only 1 in a red circle. And you won't be quite convinced that there is something here. If I magnify it, you can perhaps convince yourself, but a more convincing way would be, let me see if I can make that work. Go to the next page. I may have to stop sharing here for a minute for it to allow me to go back. In the next screen, I collapse all 13 filters. I make it a false color image. And you can now see that there's an object here, redshift 8, 9, and 11 inside that circle. It's faint. And you need to remember that redshift 11 means out of 12 filters, nothing was seen except for the reddest filter, in this case, 1.6 microns. And for redshift 9, nothing was seen in the bluest 9 filters, but only a detection in the reddest 2. Redshift 8, only a detection in the reddest 3 filters. So this is how we do our redshift. You know, for some reason, need to get that back to normal. We need to use a set of filters to measure these redshifts. Let me, for the sake of how we're doing with time, we have 10 minutes left, skip some of the technical charts. And let me get straight to the gist of the gravitational lensing and talk to you about this concept of lensing to not only observe galaxies directly, which will be magnified in their brightness, which of course helps the detection, but also individual stars directly. And that's something new. Albert Einstein was actually quite irritated about having predicted the concept of gravitational lensing because he didn't think it could ever be observed 100 years ago. But one of his colleagues prompted him to make the calculation. He did the calculation, published it. He got it all right. But he started opening up the paper by saying, well, I didn't really want to do this, but I will do it to pacify my colleague. So let me, sorry, I have to do this again because for some reason, it doesn't want to go back to the next page. So here's this massive cluster of galaxies, again, a couple of arc minutes across, 10 to the 15 solar masses. So these are now like the big cities in the universe with all their suburbs. And here's a blue galaxy, a redshift 1.5 or so. It's 4 times repeated, 4 images that are gravitationally magnified of the same galaxy. The galaxy is originally here somewhere, but the light goes around the cluster and then via 4 different paths. And then you see the thing in 4 different directions. Here's another one, 1, 1, 1, 1, all part of the same galaxy, but gravitationally magnified. Here's another one, red, red, and a counter image over here somewhere. There's another counter image. So there's usually 4, sometimes 5 images. There could be one right in the center, which is the original. And the beauty of this is the further out you go in redshift, the easier this gets because the objects will be spread out further behind the cluster, so they're not confused with the intercluster light over here. There's a fair amount of foreground light that makes it harder to discover these lensed galaxies. So these kinds of things that we're after, they're quite far away. This is galaxy redshift 5, I think, and there's some others even at higher redshift that get highly magnified. Now, for an object-tipped galaxy, half an arc second across, the magnification factor is about a factor of 10 or 20. These are the magnifying contours. We call them the critical curves. You need to make an accurate mass model of all the galaxies, and you sort of assume that light traces the mass. And then you use all these image pairs or quadruplets to optimize your model. And once you do that well, you get these contours, one for redshift 2 and one for higher redshift 4 or 5 over here, I think. And here's where it's done for redshift 10. So this is not an actual image, but this is the lensing contour for a cluster redshift half, max 1149, with all the giant galaxies, you know, at these dark blobs. There's actually a little bit of demagnification at the positions of the foreground cluster galaxies themselves. But around these contours is where you get maximum magnification. Now, the trick is that because the angular size distance scales with redshift, it's like the small angle approximation we teach in physics, but it's not a linear scaling. It actually reaches a minimum around redshift 1.65. And then at higher redshifts, galaxies, when you place them further away from you, they actually get larger in the sky. And therefore, the original landscape at redshift 10, this kite-looking thing over here, I call it my spider web, Black Widow spider web. That's the gravitational landscape in which most of the magnification occurs at redshift 10. And this landscape has the ironic property that near the edges of the Black Widow spider web, the magnification is almost infinity. It goes as the distance to this edge, this caustic, to the -1/2 power. So if you have a galaxy half an arc second across, you get a magnification factor of a couple of dozen, which is interesting. It helps detecting it. But if you get a star at this caustic at redshift 10, that's 10 to the -11 arc seconds across, a star like the sun, you can get a magnification that's higher than 100,000, maybe even more. And in astronomical units, that will be 12.5 magnitudes or more. Now, and this would then result in a temporary magnification of that star for a couple of months, for, you know, more than a factor of 10,000 above the detection limit. And this was something completely unheard of until it was first discovered with Hubble a few years ago. But you really can get these extreme magnifications. And that's because this spider webs moves at about 1,000 kilometers a second in the large-scale structured universe across the distant stars and galaxies. So once upon a time, when you go across this spider web, you will see for about 3 or 4 months, you'll see a star flare up by these kinds of magnitudes. And this has been observed with Hubble a couple of times. Adam Rees and company were actually looking for lensed supernovae, which they found one of them in one of these lensed clusters. But they also found this object here that was barely there in 2014 and much brighter in 2016. And it's right on the critical curve, so in the source plane on the caustic. And it actually, you know, this would be superluminal motion if it was true proper motion. The thing was here in 2014, and it reappeared on the other side of the caustic in 2016. And it could not have possibly moved for real because that would be faster than the speed of light. But because it was a caustic motion, the parity flipped. You observed it from here early on, from there later on. And then they knew that was the right explanation. This thing moved across the caustic. And because it was finite in angular size, it had a finite magnification. But it was a factor of 2,000. A star, you know, 20,000 degree Kelvin star at redshift 1.5, a really major discovery a few years ago. Around that time, our predictive paper came out. Here's how we measure the redshift of that star. We have a whole bunch of filters. We measure the clear Balmer break at 3,648 angstroms of the hydrogen atom, which predominantly makes up the atmospheres of these stars. And lo and behold, the break is there. The redshift is pretty solid. But when you monitor as a function of date, time, the brightness of this star, it wasn't constant. It started flaring up. And when the caustic is clean, it has no microlensing in front of it, you get this nice, line of extremely high magnification up to factors of 10,000. When there is microlensing by low mass stars in the cluster foreground, you start diluting this line a little bit, so you can get many more of these lower peaks. But in any case, you can stretch the magnification out from a factor of 10,000 in a few months to a factor of a few thousand over a few years. And we are now observing this more routinely. I'll spare you all the details. Here's another one observed by two teams, redshift 0.94, about half a Hubble time away. And we have now a whole bunch of these clusters that we think are good enough to start observing these first stars. Here's the luminosity versus temperature diagram of these first stars. For the sake of completeness, I'll spare the details, but only the most massive stars, which get the hottest about 100,000 degrees for a few hundred solar masses, that leave, of course, LIGO mass black holes behind. Those are the ones with the stars and their black hole accretion disks that we hope to observe routinely, following the same principle. The black hole accretion disks, of course, get a lot hotter than 100,000 degrees in the center. They will emit X-rays, which will even give more magnification because it's so tiny, such high surface brightness. And we hope to see these things routinely, about 1 per 3 clusters if we observe it a few times a year. So we're going to observe up to 10 clusters a few times a year. And we hope to get lucky. These are my conclusions, by observing a number of these caustic transits at redshift bigger than 6 or 7, and therefore see the first stars directly. So I'll put up my conclusions here. We hope to see the first stars and their stellar mass black holes directly through these caustic transits. We think this is possible. We have seen a few lower redshift cases. I can't talk about it yet, but there's a Nature paper coming out with an even much higher redshift caustic transit, also done with Hubble. Hubble runs out of steam at redshift 6. James Webb will need to take over at redshift 7 and beyond. So don't miss the boat on writing your proposals. The next round of proposals is due in November next year. It will be a feeding frenzy, and I'll leave it at that, and I'll be around to answer some more questions. Thank you very much, Igor, and everybody.
Thank you, Roger, for a nice talk. Now we will have some time for questions. So if you have a question, please raise the hand. And in the meantime, let me start with a very simple question of my own that I had. When you were talking about this caustic magnification, generally, well, it's a big magnifying glass basically, but when you have caustics in optics, typically the image, the shape and everything is very much distorted. So which physics information is preserved by that and which one is messed up?
Well, the sizes are certainly highly disturbed. So you normally don't get into business to measure the galaxy sizes, because you can see here they're extremely stretched. You can see on some of these distant arclets, they're spread over many pixels. And so the surface brightness, the brightness per pixel is to first order constant, but you get so many pixels that you really need to model what the local gravitational distortion is of that cluster to see what the true sizes are. In the other direction, perpendicular to that, the sizes are far more accurate. So you get basically a one-dimensional accurate size measurement and another one that highly depends on the magnification model. Yeah, we do this modeling over here and over here with different models, and they're more or less consistent to within a factor of 2 or so. They're not perfect, but they get better over time, and they're done on supercomputers.
But what about the spectra?
Yeah, so I had some spare charts on that. The spectra are actually a little easier to do. Let me see if I. So a spectrum of a redshift 7 or 8 source, let's take this blue spectrum, it's very hot, and then it drops down basically to 0, because the 1216 angstroms in the hydrogen atom, as you know, if that lifts it up from the first to the second shell, the electron, and if you give it 912 angstroms of energy, you ionize it. But it's this wavelength 1216 that already makes all the light. And of course, this curve would normally continue for a hot star, but all the light to the left of 1216 gets absorbed. And so when it's redshifted by, let's say, 1 plus e is 9, redshift 8, there will be no detection in this filter, half a detection in this filter, and then a lot more detections in the redder filters. And that gives you a rough spectrum, like I showed earlier, that gives you a pretty accurate estimate of redshift. Now, with the spectrographs, we can actually start looking for the hydrogen absorption features, like the Lyman series absorption lines and other carbon and oxygen features, if it's already there in the atmospheres of these stars. And that's what the two spectrographs, the NIRSpec and the MIRI spectrograph, will do, and also the nearest slit spectrograph. Yeah, great question.
Okay, let's see. Any other questions? Thomas Schaefer, please.
Yeah, I'm sorry to come back to the device.
Sure.
So one of the beautiful things about Hubble is that it ended up lasting so much longer than anybody ever thought it would. But of course, that was helped by the fact that it could be serviced. So what is the thing that somehow most immediately limits the lifetime of JWST?
So the paradigm there is different for Webb compared to Hubble, right? Hubble, in fact, we would have lost it a long time ago if it had not been for the servicing. We've had 6 shuttle missions, 1 for launch, and 5 servicing missions. And each one of those replaced parts that were made in the 80s or 90s. And they had, technically speaking, this is engineering, a mean time between failures of 5 years, but none of them really lived longer than 3.5 years. And they got away with it because they always had a spare part, a gyro, and another gyro for the same direction. So if one gyro failed, you had another gyro to work with. But then you had to come back within 5 years with a shuttle to replace things. And they've done that regularly. With Webb, it's different. We can go to L2, but it's not designed for that and would have made it even more expensive and take longer. So instead, it has lots of redundant parts, 6 gyros, 6 reaction wheels, and everything is top of the line in the industry. Let me give you the example of the reaction wheels. They're made by Rockwell Collins in Heidelberg, just off the Autobahnkreuz. And so in 2014, I decided to pay them a visit to see how good these things were, right? And because the Kepler mission had just lost its reaction wheels to the point it could no longer point in the sky. They used the reaction wheels to point by slewing the telescope in the opposite direction. And so my wife and I gave a popular version of this talk first, and then they put us in bunny suits in the clean room to look at their reaction wheels. And they're about a little less than 1 meter in size, 20 kilograms, basically a small suitcase. And they are made with ball bearings to spin very accurately for a very long time with a spin rate that's adjustable. So how reliable is this? Well, they in the 90s, when watches went from mechanical to electronic, they had bought up the Swiss watchmakers from Basel to make these micro precision ball bearings with sub-micron precision. So these reaction wheels in Rockwell Collins were certified for 15 years. But say we'll give you a 50% discount. They actually run for 22.5 years on average. Well, what does that mean? Say, well, let's bring you to the testing chamber. And so we went to a chamber that's bigger than one of our classrooms, and a whole bunch of benches with reaction wheels spinning. And so many dozens of them. So I asked them, this was in 2014, which one will we get? He said, well, the generation in the corner there. I looked at that thing and said, you mean that old piece of crap? He said, yeah, been sitting there for since 1972, and it's still spinning and been there for 40 years. And so they have statistics of, which one of the reaction wheels will live the longest. And those are the ones we purchased, and we got 6 of them. So it is likely that after 5 years requirement, 10 years goal, sometimes in that range or beyond, hopefully after 12 to 14 years when we run out of propellant, we will lose 1 or 2 reaction wheels. But as long as not 2 of the same, we can still be operational. Does that make sense?
Yeah, but so the most immediate thing is propellant. You run out of propellant?
Well, yeah. So what happens if you, let me see, it's not very kind for me demagnifying, but when you go to this north ecliptic pole, for instance, or anywhere in the sky on this chart, you don't need to use propellant to steer. The telescope gets steered by the reaction wheel. So if you want to go from here to there, you just spin the reaction wheels differently. And then the gyros will do the fine pointing. But if you point at a field too long, let's say if I owned a telescope and I pointed for 1,000 hours here in my favorite north ecliptic pole field, because I was so anxious to find all these high redshift supernovae, then your reaction wheel starts spinning up to the maximum. And now you have to use propellant to dump their angular momentum. See, with Hubble, you go around the Earth every 96 minutes, and you can dump the angular momentum of the reaction wheels on the Earth magnetic field with the magnetometers that Hubble has. Here, you're outside the Earth's magnetic field, so you can't use magnetic forces to dump the angular momentum, so you have to use propellant. The only other alternative is to not point here for 1,000 hours, but only for 100 hours, and then spend a half hour slewing to observe here on the other side for 100 hours. And that would unspin the reaction wheel sufficiently that you save yourself propellant. So you're going to have a very, clever AI calculated pointing schedule that maximizes the life of the propellant and minimizes the spin up of the reaction wheels. Does that make sense?
Yeah, thanks.
Yeah, excellent question.
Okay, next question is Paul Danilovich.
Yeah, my connection may be bad. My question is about the Lagrange point. So from school, I remember that Lagrange points tend to accumulate debris. Is that of a concern or not?
Yes, that is very true, but only in L4, L5. So L4, L5 are at the 60-degree points. The Earth is here, that's the moon's orbit. The sun is 100 times further away than the moon in the other direction. And L4, L5 are at 60 degrees with the Earth-Sun L4 triangle. And those are the only two stable Lagrange points. So that's where you can accumulate asteroids and dust and crap. L2 is unstable. So if you do nothing, you drift out after a few months. And anything that gets there, like a small asteroid or cosmic dust, will also drift out. So you need to understand the volume we describe here is 10 to the 18 kilometers, cubic kilometers. It's 1 million kilometers in each of the 3 cardinal directions. And there's a couple of spacecraft out there, like the old Planck, Herschel, and WMAP, and Gaia spacecraft. But it's only a dozen spacecraft in 10 to the 18 cubic kilometers. It's not like the 100-kilometer shell around the Earth that has 100,000 satellites. So we're not going to run into anything. Our main concern is that the sun shield will be hit by micrometeorites. And we know the micrometeorite density. So on the timescale of 10 years, this sun shield will have some holes in it. It will look like an excellent road sign. But you will get a little bit of extra stray light from that. And that's something that it's designed for. Great question.
Okay.
Yeah.
Thanks.
Yeah, sure.
Wouldn't those meteoroids break the actual telescope?
Say again?
It?
Oh, the micrometeorite.
You said, yeah.
Yeah. So their size distribution is a power law with a slope of -3.5. So it goes r to the -3.5. That means of 10 microns, you get a certain amount. And 100 microns will be 3,000 times more rare. So Hubble has been hit over the course of the decades with 10 micron sized particles typically. But a centimeter sized particle would kill the telescope. A millimeter sized particle, not necessarily 100 micron sized particle, which has been hit by a number of times, wouldn't scratch the titanium very much, but create a little pothole. So eventually you will get some dents on the mirror, from 10 to 100 micron sized particles, but they won't necessarily crack the mirror. That has never happened to Hubble in 31 years in orbit. I can show you an image of that, but I have to dig.
What I meant is a simpler thing, those dents, since you were saying that you have to perfected to nanometers. If you have a little dent, it will be.
Yeah. You do need to do the tilt and the tip tilt and the translation of the mirrors. You have to adjust that every 2 weeks, and a tiny amount of that is due to gravitational impacts of micrometeorites. Most of it is due to thermal changes. So that's the telescope is designed for that. Yeah.
I see.
Yeah, good question.
Okay. Thanks. I don't see any other questions, so this is the last call. If you have any questions, in the meantime, I would like to use this opportunity and thank you, Roger, for a very nice talk.
All right. Well, thanks for inviting me.